This is Learning Assessment Problem 917. The problem-solving strategy here is that of complex power calculations. The problem provides some information about load and the transmission line impedance connecting that load to the input source, and we are asked to determine the line voltage and the power factor at the input end of this transmission line. First, we'll sketch the complex power triangle representation at the load end of the problem. Here the complex power S sub L is represented by the real component P sub L, real power, and the quadrature component of the complex power JQ sub L. The power factor at the load end of this circuit is equal to the cosine of that angle associated with the complex power theta sub L. And this gives us that theta sub L is equal to the inverse cosine of 0.85, or theta sub L equals 31.79 degrees. The magnitude of the complex power, which is known as the apparent power, will be equal to the real component divided by the cosine of that angle theta sub L, which is the real power consumed in the load divided by the power factor, and that in this case will be 60 kilowatts divided by 0.85, which is equal to 70.59 kilovolt amperes for the magnitude of the complex power. In polar form then, the complex power becomes 70.59 at an angle of 31.79 kilovolt amperes. Complex power can also be obtained by calculating the product of the load voltage phasor times the complex conjugate of the load current phasor. We can use this to solve for the expression for the load current phasor being equal to the complex conjugate of the quotient of the complex power divided by the phasor voltage at the load. It should be noted that the complex power symbol S sub L with a vector bar over it is not a phasor quantity. It's just a complex plane quantity. We can then calculate the load current phasor. This is the ratio of the complex power to the load voltage, and that is equal to 320.86 at an angle of minus 31.79 degrees amps, and those would be RMS amperes. The negative sign associated with the phase angle of the current comes about from the complex conjugate operation in the calculation. The equivalent circuit for this problem is shown here. We have the load impedance connected to the input voltage source through the transmission line impedance. So we have V sub L at the load and a voltage drop along the transmission line, V line, and we have the load current, I sub L, flowing through the transmission line. The voltage drop along the transmission line, V sub line, is equal to the impedance of that transmission line times the load current flowing through it, where the transmission line impedance in polar form is 0.216 at an angle of 56.31 degrees ohms. Then the calculation for that line voltage drop is equal to, which is equal to 63.14 plus J 28.8 volts in the rectangular form. Then we can calculate the input voltage as the sum of the line voltage phasor plus the load voltage phasor, or Vn is equal to 284.6 at an angle of 5.81 degrees volts RMS. Now we can proceed with the calculation of the power factor at the input end of this circuit. That will be defined as the cosine of the phase angle associated with the input voltage minus the phase angle associated with the current, in this case the load current. This is equal to, or the power factor at the input is equal to 0.792. And this is a lagging power factor. Lagging nature means that the current lags the voltage.